All right, today we're going to talk about convergent and divergent series, and basically we will determine if a series converges or diverges. So first, a convergent series. A convergent series is a series, an infinite series that has a sum or a limit. A divergent series is an infinite series that does not converge. So all infinite series fall into one of those categories. They are either a convergent series that has a sum or a divergent series that does not have a sum. So now, even though this is a new idea to us, we have background information. So here it says determine the convergence of the series. So we're looking at this series, so 2 plus 4 thirds plus 8 ninths plus 16 27ths, and so on. So it is an infinite series. Specifically, this is an infinite geometric series. So we've spent some time talking about infinite geometric series and how they behave. This one's common ratio is 2/3, which means since that's between -1 and 1, we can find the sum. There is a sum, which means this series converges. So we don't necessarily have to find the sum. Just knowing that I could, if I wanted to, is enough information to tell me that this series converges. All right, so our next example, we have the series 2 minus 4 plus 8 minus 16, which again is an infinite geometric series. This one's common ratio is -2. If we have a common ratio of -2, we cannot find the sum. There is no sum here. And just looking at the numbers, these are just going to keep getting bigger and bigger. They're going to bounce between positive and negative, but they keep getting bigger and bigger and bigger. So there's no way there's going to be a sum. And if there is no sum, we say that the series is divergent. Next series, we have 1 plus 2 plus 3 plus 4, and so on. You can probably tell just by looking at it that this series is not going to converge because the terms just keep getting bigger and bigger. This one is an arithmetic series. And by definition, an arithmetic series, we continue to add a common difference to get from term to term. So we're adding 1, so these terms are keep getting bigger and bigger and bigger. And if the terms keep getting bigger and bigger and bigger, they're not going to hit a limit. It's just going to keep going, which means this series is divergent. So what we're going to do for the rest of this is determine different ways that we can determine convergence. So the first one is infinite geometric series. So if you can identify that the series that you have is an infinite geometric series, we have two different cases. Either our common ratio is between -1 and 1, or it's not, meaning the absolute value of it is bigger than or equal to 1. In this first case, if the common ratio is between -1 and 1, we know we can find the sum, which means our series is convergent. If it is bigger than 1 or less than -1 or equal to either of those, we cannot find the sum, which means the series is divergent. So when you're asked to find the divergence or convergence of the series, if you can identify it as infinite geometric, all you have to do is identify that, what the common ratio is, and then based on that, whether it is convergent or divergent. Next, if we have an infinite arithmetic series, like I already said, by definition, you are continuing to add or subtract the same number and over. So the terms are either going to get infinitely big or they're going to get infinitely negative, which means if you're going to add those together, you cannot find a sum. So an arithmetic series is always divergent. So if it's arithmetic or geometric, we can determine what's happening. If the series, however, is not, there are a variety of different what we call tests to determine convergence. We are going to introduce two more tests. The divergence test here. Next class will be partial sums. And then some of you, if you choose to, are going to learn about the ratio and comparison tests. If you're taking calculus, there ends up being about 11 different tests for convergence. So the divergence test is the first one, and it's a fairly simple idea. It's called the nth term test because what we're going to look at is what happens to the terms as they get infinitely big, as n goes to infinity. So if the limit as n goes to infinity of an, okay, so we're looking at the terms itself. If the limit is anything but 0, that means you are adding infinitely something that is not 0. You are adding something of some quantity, which means the series has to diverge. Okay, so if the limit is anything but 0, then the series diverges. So it's called the divergence test because you will determine if it diverges. The caution, and this is going to be a little counterintuitive based on what I've been telling you over the last couple weeks, but if the limit as n goes to infinity of the nth term does equal 0, the series could converge, but it doesn't necessarily. So if this is the case, it could converge or diverge. And like I said, this is counterintuitive because I've said, well, if the terms get smaller and smaller and smaller, then it arrives at a sum. This is not always the case. That is the case with geometric series. So if the terms are getting smaller in a geometric series, it will converge, just the nature of how those work. But not every series whose terms get smaller and smaller and smaller will have a sum or will converge. There are some cases where even though the terms are getting smaller and smaller and smaller, they're just not getting smaller fast enough to make it so that they have a sum. So we will see some of those eventually, but that's a little bit counterintuitive. So there's only two cases. If you get anything but 0, it diverges. If you get 0, we say that the test is inconclusive. Okay, test is inconclusive. So if you were asked to determine the convergence and you found that the limit was 0, it would require more investigation into one of the other tests that I'll show you over the next coming days. So what we're going to do is use the limit as n goes to infinity of an, that's the divergence test or the nth term test, to determine whether a series diverges or whether it diverges. So we're going to look at our first example. So we're going to look at the sum from 1 to infinity of 3n plus 4 over 2n minus 3. So what we're going to do is we're going to look at the limit as n goes to infinity of our nth term, which in this case, and when it's written in sigma notation, it's always that general formula. So we're looking at the limit as n goes to infinity of 3n plus 4 over 2n minus 3. Well, we look at this is a rational function, so the degree is the same on the top and the bottom, so this limit is 3/2. Okay, 3/2 is not equal to 0. Okay, in order for a series to even potentially converge, the limit has to go to 0. Those terms have to get smaller and smaller and smaller. This is saying if I plug in a million, my millionth term is basically going to be 3/2. So I'm going to be adding 3/2 plus 3/2 plus 3/2 infinitely. So since it does not equal 0, this series diverges. Okay, so my next example is from 1 to infinity of 1 over n squared. So we are investigating the limit as n goes to infinity of an, which for this one is the limit as n goes to infinity of 1 over n squared. Well, this one, the degree is bigger on the bottom, so this limit is 0, which means it could converge, but we don't have enough information. This test will never say something converges. It's always divergent or inconclusive. So this one could converge, could diverge. If you were asked to find if it does, then you would have to move on to a different test. But for right now, all we know is it might converge, but it still might diverge. So out of the convergence test or the divergence test, these are the only two scenarios. Either you get something that is 0 and it's inconclusive, or you get something that is not 0, which means it diverges. Okay, so I'm going to do one more of these because this one kind of comes up. It's kind of a weird little series, because if I plug in 1, we're going to get -1. If I plug in 2, we're going to get 1. 3, you're going to get -1. So the series bounces back and forth. If I looked at the limit as n goes to infinity of my nth term, so -1 to the n, this thing bounces. It is either 1 or it is -1. And since it does not equal one single number, this limit does not exist. Okay, so this series diverges because guess what? dne does not equal 0. So this one would bounce around. It's going to bounce around between 1 and -1, and when we talk about partial sums, we'll look at what that looks like. But this series diverges because it does not go to a single value, and for us, it has to have a sum or a limit, and this one just does not. There's one last thing that I'll talk to you guys about. It's just sort of a hey, here's a fun fact. Something called the convergence theorem. This is not a test. This will not tell us if something converges or diverges. It's just sort of a fact. So the convergence theorem just says if you have a convergent series, so if the sum of your whatever your ANs is a convergent series, then that tells you that the limit has to have been 0 for the terms. The converse of that is not true. If the limit is 0, it may or may not converge. But if you know what converges, then the terms had to go to 0. Like I said, this is not a test. It's just sort of a fact. So that was your introduction to convergent and divergent series. Like I said, we will continue to add more tests over the next couple of weeks.